If I bring my hand closer to a source of heat, it gets hotter, obviously. Bring it further away, and I no longer feel that heat. But that's not the case with every heat source. For example, the sun's corona is the outermost layer of the sun's atmosphere, and the corona is much hotter than the surface of the sun. It lies above the chromosphere and extends millions of kilometers out into our solar system. Coronal light is typically obscured by radiation in the atmosphere and the glare from the solar disk. However, this is easily seen during a solar eclipse. It's that outermost ring that you see during the eclipse. Spectroscopic measurements indicate strong ionization in the corona, and plasma temperature exceeds 1 million degrees Kelvin, which is much hotter than the photosphere, which is the surface of the sun. Solar corona is broken down into three select regions. The F corona is a set of spectral absorption lines. These are formed when atoms in the solar atmosphere absorb light being emitted by the solar photosphere. As it gets further away from the sun, it transforms into what is known as zodiac light, which is sort of that faint glow that you see around the stars or before sunrise. It's recognized to arise from small dust grains orbiting the sun, and it forms a tenuous cloud throughout much of our solar system. The second is the K corona, which is a spectrum containing no major spectral features. It is sunlight that is Thomson scattered, which is elastic scattering by a free charged particle in the hot plasma of the sun's outer atmosphere. The K corona is a phenomenon of the electrons in the plasma. This term is frequently used to describe the plasma itself. And lastly, the E corona is the component of the corona with an emission line spectrum. It is a phenomenon of the ion component of the plasma as individual ions are excited by collision or absorption of the UV light. The sun's corona is much hotter by a factor from 150 to 450 than the visible surface of the sun. However, it produces about 1/1,000,000th of the visible light. The exact mechanism by which the corona is heated is still some subject of debate, but it likely includes episodic energy releases from the pervasive magnetic field and magno-hydrodynamic waves from below the outer edges of the sun's corona are constantly being transported away, creating the open magnetic flux that is entrained in the solar wind. The corona, however, is not always evenly distributed across the surface of the sun. During periods of quiet, the corona is more or less confined to the equatorial regions, with coronal holes covering the polar regions. However, during the sun's active periods, the corona is evenly distributed over the equatorial and polar regions, though it is most prominent in areas with sunspot activity. Since the solar magnetic field is continually wound up due to the faster rotation of mass at the sun's equator, sunspot activity is more pronounced at the solar maximum, where the magnetic field is more twisted. High-resolution X-ray images of the sun's corona photographed by Skylab in 1973 revealed the structure of the corona to be quite varied and complex, leading astronomers to classify various zones on the coronal disk. The regions are usually described as follows. Active regions are ensembles of loop structures connecting points of opposite magnetic polarity in the photosphere, so-called coronal loops. They generally distribute in two zones of activity, which are parallel to the solar equator. The average temperature is between 2 and 4 million Kelvin, while density goes from 10 to the 9th to 10 to the 10th particles per cubic centimeter. These are those solar flares, the little loops that come out the sun that you're probably thinking of. Another feature observed of the sun's corona was something called a filament cavity. Filament cavities are zones which look dark in the X-rays and are above the regions where HA filaments are observed in the chromosphere. They were first observed in two 1970 rocket flights, which also detected coronal holes. Filament cavities are cooler clouds of plasma suspended above the sun's surface by magnetic forces. The regions of intense magnetic fields look dark in images because they are empty of hot plasma. In fact, the sum of the magnetic pressure and plasma pressure must be constant everywhere on the heliosphere in order to have an equilibrium of configuration. Where the magnetic field is higher, the plasma must be cooler or less dense. Bright points are small active regions found on the solar disk. X-ray bright points were first detected on April 8, 1969 during a rocket flight. Coronal holes are unipolar regions which look dark in the X-ray since they do not emit much radiation. These are wide zones of the sun where the magnetic field is unipolar and opens toward interplanetary space. The high-speed solar wind arises mainly from these regions. In the UV images of the coronal holes, some small structures simulated to elongated bubbles are often seen as they were suspended in the solar wind. These are coronal plumes. More precisely, they are long, thin streamers that project outward from the sun's north and south poles. The solar regions which are not part of active regions and coronal holes are commonly identified as the quiet sun. The equatorial region has faster rotation speed than the polar zones. The result of the sun's different rotation is that the active regions always arise in two bands parallel to the equator, and their extension increases during the period of maximum in the solar cycle, while they almost disappear during each minimum. Alphen surface, I don't know if I said that right, I'll have it up on screen, is the boundary separating the corona from the solar wind, defined as where the coronal plasma's Alphen speed and the large-scale solar wind speed are equal. Researchers were unsure exactly where the Alphen critical surface on the sun lay. Based on remote images of the corona, estimates have put it somewhere between 10 and 20 solar radii on the surface of the sun. During its 8th flyby of the sun, NASA's Parker Solar Probe encountered the specific magnetic and particle conditions at 18.8 solar radii. I'm not sure if I'm saying that word right. That indicated that it penetrated the Alphen surface. And in this region is where the solar flares occur. Flares take place in active regions and are characterized by sudden increase of radiative flux emitted from small regions of the corona. They are very complex phenomena visible at different wavelengths. They involve several zones of the solar atmosphere and many physical effects, thermal and non-thermal. Sometimes wide reconnections of the magnetic field lines with material expulsion. Flares are an impulsive phenomena with an average duration of about 15 minutes. And the most energetic of these events can last up to several hours. Flares produce a high and rapid increase of density and temperature. An emission in white light is seldom observed. Usually flares are seen at extreme UV wavelengths and into the X-rays, often accompanying large solar flares and prominences or coronal mass ejections. These are enormous emissions of coronal material and magnetic field that travel outward from the sun at upwards of 3,000 kilometers per second, containing roughly 10 times the energy of the solar flare or prominence that accompanies them. Some larger CMEs can propel hundreds of millions of tons of material into interplanetary space at roughly 1.5 million kilometers per hour. The matter of the corona is in the state of plasma at the very high temperature of a few million Kelvin and at the very low density of 10 to the order of 15 particles per I'll have the equation on screen. The composition is similar to that of the sun's interior, mainly hydrogen, but with much greater ionization of its heavier elements than found of that in the photosphere. Corona behaves like a gas. The pressure in the corona is about only 0.1 to 0.6 in active regions, where the atmospheric pressure is about 100 kPa millions higher on the surface. However, it is not properly a gas because it is made of charged particles. Basically, protons and electrons moving at different velocities. Supposing they have the same kinetic energy on average, electrons have a mass roughly 1,800 times smaller than protons. Therefore, they acquire more velocity. Metal ions are always slower. The fact has relevant physical consequences either on radiative processes or on thermal conduction. Furthermore, the presence of electric charges induces the generation of electric currents and high magnetic fields. Magnetohydrodynamic waves can also propagate in this plasma, even though it is still not clear how they can be transmitted or generated within the corona. In the corona, thermal conduction occurs from the external, hotter atmosphere towards the inner, cooler layers. Responsible for the diffusion process of the heat are the electrons, which are much lighter than the ions and move faster. There's a magnetic field. The thermal conductivity of the plasma becomes higher in the direction which is parallel to the field lines rather than in the perpendicular direction. A charged particle moving in the direction perpendicular to the magnetic field is subject to the Lorentz force, which is normal to the plane individuated by the velocity and magnetic field. This force bends to the path of the particle. In general, the Lorentz force constrains them to bend and move along spirals around the field lines at the cyclotron frequency. Collisions between particles are very frequent. They are scattered in every direction. This happens in the photosphere where plasma carries the magnetic field in its motion. In the corona, the average of the free path of the electrons is order of kilometers, even more so. Each electron can do a helicoidal motion long before scattering after a collision. Therefore, the heat transfer is enhanced along the magnetic field lines and inhibited in the perpendicular direction. The method of studying this is known as coronal seismology. Coronal seismology is a method of studying the plasma of the solar corona using magnetohydrodynamic waves, or MHD, studies the dynamics of electrically conducting fluids. In this case, the fluid is the coronal plasma. The problem first emerged after the identification of unknown spectral lines in the solar spectrum with highly ionized iron and calcium atoms. The comparison of the coronal and photospheric temperatures of 6,000 kelvins leads to the question of how the 200 times hotter coronal temperature can be maintained. The primary concern is with how the energy is transported up into the corona and then converted into heat within a few solar radii. The high temperatures require energy to be carried from the solar interior to the corona by a non-thermal process. Because the second law of thermodynamics prevents heat from the high temperatures require energy to be carried from the solar interior to the corona by non-thermal processes. Because the second law of thermodynamics prevents heat from flowing directly from the solar photosphere, which is about 5,800 Kelvin, to the much hotter corona at about 1.3 million kelvins, the photosphere and the corona. The thin region through which the temperature increases is known as the transition region. It ranges from only 10 to hundreds of kilometers thick. Energy cannot be transferred from the cooler photosphere to the corona by conventional heat transfer, as this would violate the second law of thermodynamics. An analogy of this would be a light bulb raising the temperature of the air surrounding it to something greater than the glass's surface. The amount of power required to heat the solar corona can easily be calculated as the difference between coronal radiative losses and heating by thermal conduction towards the chromosphere through the transition region is about 1 kilowatt for every square meter of surface area on the sun's chromosphere, or 1/40,000th of the amount of light energy that escapes the sun. There have been two main prevalent theories that have survived over the years, so I'm going to go over those two now. Wave heating theory was proposed in 1949 by Hervé Schatzman. Proposes that the waves carry energy from the solar interior to the solar chromosphere and corona. The sun is made of plasma rather than ordinary gas, so it supports several types of waves analogous to sound waves in the air. Magnetoacoustic waves are sound waves that have been modified by the presence of a magnetic field, and Alvin waves are similar to ultra-low frequency radio waves that have been modified by interaction with matter in plasma. Both types of waves can be launched by turbulence of granulation and supergranulation at the solar photosphere. and both types of waves can carry energy for some distance through the solar atmosphere before turning into shock waves that dissipate their energy as heat. The problem with this theory is the delivery of the heat to the appropriate place. Magnetoacoustic waves cannot carry sufficient energy upward through the chromosphere to the corona because of the low pressure present in the chromosphere and because they tend to be reflected back to the photosphere. Alpha waves cannot carry enough energy. Alpha waves can carry enough energy but do not dissipate that energy rapidly enough once they enter the corona. Waves in plasmas are notoriously difficult to understand and describe analytically. Computer simulations carried out by Thomas Bogdan in 2003 seem to show that alpha waves can transmute into other waves at the base of the corona, providing a pathway that can carry large amounts of energy from the photosphere through the chromosphere in a transition region and finally into the corona where it dissipates as heat. Recently, alphanic motions have been found in the lower solar atmosphere and also in the quiet sun region, in coronal holes and in active regions using the observations with AIA on board the Solar Dynamics Observatory. These alphanic oscillations have significant power and seem to be connected to the chromospheric alphanic oscillations previously reported in the Hinode spacecraft. The second theory is the magnetic reconnection theory. The magnetic reconnection theory relies on solar magnetic fields to induce electric currents in the solar corona. The currents then collapse suddenly, releasing energy as heat and wave energy into the corona. This process is called reconnection because of the very particular way that magnetic fields behave in plasma. In plasma, magnetic field lines are normally tied to individual pieces of matter, so that the topology of the magnetic field remains the same. If a particular north and south magnetic pole are connected by a single field line, then even if the plasma is stirred or if the magnetics are moved around, that field line will continue to connect those particular poles. The connection is maintained by electric currents that are induced in the plasma. Under certain conditions, the electric currents can collapse, allowing the magnetic field to reconnect to other magnetic poles and release that wave energy in the process. Magnetic reconnection is hypothesized to be the mechanism behind solar flares. Furthermore, the surface of the sun is covered with millions of small magnetized regions, ranging from 50 to 1,000 kilometers across. These small magnetic poles are buffed and churned by constant granulation. And a field in the solar corona must undergo nearly constant reconnection to match the motion of its magnetic carpet. So the energy released by the reconnection is a natural candidate for the coronal heat, perhaps a series of microflares that individually provide very little energy but together account for that required energy. Just something that I found interesting. It's still something that's being researched and observed, but I remember always being interested in the solar flares every time, because you'd always hear those stories about, oh, the solar flare is going to knock out all your internet devices, it's going to knock out all your electronics. Anyways, thank you guys for watching. Until next time.